Hello students, in this lecture we'll study about biasing of enhancement MOSFET. In the last lecture we studied about biasing of a JFET. Three different types of biasing we studied. One is fixed bias, self bias, combination of self and fixed bias. So I am taking into consideration N-channel MOSFET. N-channel MOSFET is taken into consideration. So figure shows biased configuration of N-channel MOSFET. As you can see from the figure, it is a combination of both fixed and self-bias circuit. So this is the voltage divider circuit, which can be remodeled with a Thevenin's equivalent circuit where VGG is equal to VDD into R2 by R1 plus R2 and RG is equal to R1 R2 by R1 plus R2. And this figure shows the transfer characteristics of a N-channel MOSFET. So in MOSFET, enhancement MOSFET, you can see the transfer characteristics are very much different from the JFET or depletion MOSFET, and the current ID is also different compared to JFET and enhancement MOSFET. So in enhancement MOSFET, if you make RS is equal to 0 volts, 0 ohms. Okay, so when if you make RS is equal to 0 ohms and we got ID value, okay, we got ID value. So if by any chance the transfer characteristics will vary, the Q point will vary over a wide range. Therefore, fixed bias in N-channel enhancement MOSFET is not possible. So we never make this RS is equal to 0. So only biasing circuit which is valid for enhancement MOSFET is shown in the figure. So unlike JFET, fixed bias circuit in enhancement MOSFET is not possible because for any change in the transfer characteristics, characteristics, it would result into significant change in the Q point. So for this reason, we will make RS always RS greater than 0. So if you carefully observe this circuit, it is a combination of fixed bias and self bias circuit. So how to obtain a Q point? We have to draw the transfer characteristics and then we have to draw the line which will represent these. ID is equal to minus VGS by RS plus VGG by RS. So the derivation for this equation we have explained for a JFET. We need to resolve this circuit with respect to Thevenin's equivalent circuit, then apply the KVL to the left hand loop, and after that apply the KVL to the right hand loop. You will get this equation ID is equal to minus VGS by RS plus VGG by RG. The conditions which we have considered in JFET remain same. So the conditions is an IG is equal to 0, IG into RG will be 0, then VGG is equal to minus V plus VG, and RS is equal to VS is equal to ID into RS. So the conditions will remain same for the derivation of this equation for ID. The condition is your IG is equal to 0, ID is equal to IS, voltage across the source VS is equal to ID into RS, and VG is equal to minus VGG. So let us solve the enhancement MOSFET biasing, a simple problem. So the figure shows MOSFET enhancement MOSFET circuit with AC supply connected to the amplifier via capacitor, coupling capacitor, and this is a bypass capacitor. So we are going to do only DC analysis. While doing the AC and DC analysis, we will neglect the AC sources because in DC analysis, capacitor acts like a open circuit. So the DC equivalent of the amplifier using an enhancement MOSFET is shown in this figure. So given your threshold voltage, the voltage above which channel is formed is 2 volts, and the K value used in ID calculation. Remember, in enhancement MOSFET, ID is equal to K into VGS minus VT whole square. K is given as 2.5 milliampere per volt second, and R1 is 1 mega ohm, R2 is 2 mega ohm, and VDD is 2 volts. Let us determine the values of RD and RS so that MOSFET will be biased in active region. Given IDQ is 4 milliamperes, VDSQ is 6 volts. Just let us recall what is the condition for the enhancement MOSFET to be in active region is VDS should be greater than VGS minus VT, not VP, VGS minus VT. Okay, and your VGS should be greater than VT. These are the two conditions which we have to verify to find out whether enhancement MOSFET is operating in active region or not. So we have to redraw this circuit and obtain the DC equivalent circuit. So what will be the formula for VGG? VGG will be VDD into R2 by R1 plus R2. The formula for RG will be R1 R2 by R1 plus R2. Once we got equivalent circuit, DC equivalent circuit, then we can apply KVL to this circuit with the assumption that IG is equal to 0 amperes. IG is equal to 0 amperes. So drop in IG RG is equal to 0. So first step is calculation of VGG. The VGG is calculated with the formula VDD into R2 by R1 plus R2, which will get 8 volts. Then second is calculation of RG. The RG is R1, R2 are in parallel together. Then you are going to get 667 kilo amperes. Then ID Q is given. So ID is equal to IDQ, which is equal to 4 milliamperes. So from the base, let us assume now enhancement MOSFET is operating in active region. The formula for ID in active region is K into VGS minus VT whole square. So ID is given, K is given, VGS we need to determine, VT is given. So using this formula, VGS will be taking the square on this ID, root of ID, and taking K downside. Okay, so VT plus root of ID by K, substituting the values of VT, that is 2 volts, ID 4 milliamperes, K 2.5 milliampere per volt square, we will get VGS is equal to 6 volts. I'll repeat once again. The enhancement MOSFET is considered in active region. Then ID is equal to K into VGS minus VT whole square. ID is given as 4 milliamperes. K is given as 2.5 milliampere per volt square. VG is given as 2 volts. And unknown, VT is given as 2 volts. Unknown is VGS. Substituting this in this equation, we got VGS is equal to 6 volts. But the problem he has asked to determine the values of RD and RS such that MOSFET is operating in active region. So in order to find out the value of RS, we need to apply the KVL in this equation. If you write a KVL equation for this loop, it is minus VGG plus IGRG plus VGS plus ID into RS is equal to 0. So as IGRG is 0, so the equation will become minus VGG plus VGS into IDRS. So keeping this, then what is the equation for RS? RS will be minus VGG taken on the right hand side plus VGG minus VGS by ID is equal to RS. So substituting, we have applied the KVL equation and we got RS is equal to VGG minus VGS by ID. Then we will get RS is equal to 500 ohms. So once we got the RS value, we can determine the VS value. VS value is voltage at source with respect to ground. There are two ways of finding out VS value. Either I can multiply ID into RS, to get VS. So ID is how much? ID is 4 milliamperes into RS to 500 ohms. So thereby you will get 2 volts. 500 into 4 into 10 power minus 3, you will get 2 volts. Other way is that we can apply KVL, minus VGG plus VGS plus VS is equal to 0. So VS is equal to VGG minus VGS, that is 2 volts. Then we need to determine this RD. So in order to determine this RD, we need to apply KVL to this equation. So let us go for the nodal analysis. Let us consider this is one node, this is another node, and current is flowing from VDD to this node. So what is the voltage of this node? Plus VDS plus VS. So the current flowing through RD is VDD minus of VDS plus ds divided by RD. So we require RD. So RD will become RD is equal to VDD minus of this entire voltage, that is VDS plus ds divided by ID. You'll get RD is equal to 1 kilo ohm. Now we have to verify whether our assumption is correct or wrong. Since given VGS is 6 volts, 6 volts is greater than VT, first condition is satisfied. What is the first condition? Your VGS should be positive and it should be greater than threshold voltage. Second condition is VDS should be greater than VGS minus VT. What is the VGS? We got 6 volts. And what is VT2? 4 volts. So your VDS, whatever the VDS value which they have given is 6 volts, is greater than 4 volts. So active region operation is confirmed. So I'll just summarize. In enhancement MOSFET, we cannot have a fixed bias. Only the biasing possible is combination of fixed and self-bias circuit. So we have to take into consideration IG is equal to 0 and do the circuit analysis. Thereby we can determine the values of RD and RS so that enhancement MOSFET can operate in active region. Let us go for another topology or another biasing possible in MOSFET is feedback biasing. Feedback biasing. You can see in the feedback biasing there is no RS. There is no RS, but there is no RS, but you can see yeah. In this, there is a feedback resistance connected between RD and G. Okay, so this is called as a feedback resistance. Therefore, this circuit is called as a feedback biasing of enhancement MOSFET. So when you are doing a biasing, we have to make sure that enhancement is operating in active region. So what are the conditions for the enhancement MOSFET operating in active region? Your VGS should be greater than VT and your VDS should be greater than VGS minus VT. Now, as you are connecting VGS to this, if you apply KVL to this enhancement MOSFET, VGS is equal to VDS. VGS is equal to VDS. So when VGS is equal to VDS, then yeah, then VGS is equal to you can see VGS is VDS is what is the condition for the MOSFET to be operating in active region? VDS should be greater than VGS minus VT and VGS should be greater than VT. Since your IG is 0 and VDS is equal to VGS. So substituting in this formula, VDS is equal to VGS minus VT, I can substitute in the place of VDS, VGS itself. So VGS will be obviously greater than VGS minus VT because VT is always positive. So therefore, amplifier guarantees that your enhancement MOSFET is operating in active region. So for any increase, how it will regulate the increase in ID? So for any increase in ID, as ID increases, as ID increases, you know that VGS is equal to VDS. So what is the formula for VDS? VDS is equal to VDD minus IDRD. VDD minus IDRD. As ID increases, this IDRD also increases. Then as IDRD increases, this VDS decreases. As VDS decreases, VGS decreases. So if you just remember the formula for ID is equal to K into VGS minus VT whole square. So increase in ID is regulated by decrease in VGS. Therefore, any increase in ID because of any external factors, the decrease in VG will regulate, and this feedback amplifier will try to make this ID a fixed value. Therefore, Q point is remaining stable. This results into stable operation of feedback amplifier. So by connecting the gate to the drain using a feedback resistance RF, we can regulate the increase in ID by decrease in VGS. Since IG is equal to 0, in this case VGS is equal to VDS. Let us solve a small example problem on feedback biasing of enhancement MOSFET. The amplifier circuit is shown in the figure. It has K is equal to 0.25 milliamps per volt square, and the threshold voltage is 2. Suppose your RD is 1 kilo ohm and feedback resistance is 1 mega ohm and VDD is 10 volts. Find out the operating point. In simple, he is asking for operating point. So first we can apply the KVL for this equation assuming Ig is equal to 0. So applying KVL, VDD is equal to IDRD plus VDS. So from that, ID is equal to VDD minus VDS by RD. So this is a, you can even apply your nodal analysis. This Ig is equal to 0, therefore VDD minus VDS by RD is equal to ID. So this is one equation of ID. Another equation, assume that MOSFET is operating in active region. The feedback amplifier guarantees that ID is equal to K into VGS minus VT whole square. Equating equation number 1 with equation number 2. Okay, and you know VGS given in the problem. So yeah, yeah. K is given in the problem, VT is given in the problem, VDD is given in the problem, VDS is given in the problem, VDS RD. So from that, VGS is equal to plus or minus 6 volts. So students, we will solve a problem on feedback biasing of enhancement MOSFET. The feedback biasing of enhancement MOSFET circuit is shown in the figure. So we'll solve a problem on feedback biasing of enhancement MOSFET. The feedback biasing of enhancement MOSFET circuit is shown in the figure. So for an amplifier circuit shown in the figure, he has given the K value and then threshold voltage is 2 volts. Suppose RD is 1 kilo ohms and feedback amplifier feedback resistance is 1 mega ohm and VDD is 10 volts. Find out the operating point, that is VDSQ, VGSQ and IDQ. So first, in order to find out the VGS, let us apply the KVL to this loop. So if you apply KVL to this loop, the current flowing through RD, Ig is 0 anyhow, is ID is equal to VDD minus VDS by RD. So if you apply KVL, it is nothing but VDD is equal to IDRD plus VDS. From that, ID is equal to VDD minus VDS by RD. So we got one equation from ID. Now let us assume your enhancement MOSFET is operating in active region. Then ID is given by K into VGS minus VT whole square. Now this is equation number 1 and this is equation number 2. And equating these two, then K is equal to K into VGS minus VT whole square is equal to VDD minus VDS by RD. K is given in the problem, and then VGS we need to determine. VT is given as a 2 volts. VDD we need to they have given 10 volts. What is VDS? I do remember In a feedback biasing of MOSFET, VDS is equal to VGS. VDS is equal to VGS. So only unknown in this equation is VGS. On simplifying this, we'll get VGS is equal to 6 volts. So whether this assumption that it is operating in active region or is not can be verified as VGS is greater than 2 volts. So our assumption is correct. And substituting this VGS is equal to 6 volts in the above equation, we can determine the ID is equal to 4 milliamperes. Either you can use this equation number 1 or we can go for equation number 2. So finally, we have written two equations for ID and equating 1 and 2, replacing the VDS is equal to VGS. Because VDS is equal to VGS, then we will got VGS equation. Okay, so VGS we are considering as VGSQ, and then substituting that in ID, you'll get IDQ.